Okay, so today we are going to look at the next aspect of our College Board descriptions, focusing specifically on the derivative. And so you can see here we're going to look at slope of a curve at a specific point. Okay, so we're going to look at vertical tangents and where there'll be no tangents. Okay, also we're going to look at local linear approximation. And average rate of change. That was on your most recent FRQ in the practice test. And you have to be able to approximate the rate of change if I give you a table of values or a graph. Look at our first example here. And we are going to be looking at average rate of change. So we know that if we want to find the average rate of change given f of x. So basically we want to find the slope. So we would do this change in y over the change in x. Okay. Now if you want to find the average velocity given the position of a function, x of t, then you go the change in the y values over the change in x. So an example problem might be, given this function, x squared plus x, over the interval 1, 3, what is the average rate of change? So basically that rate of change says, find the slope, since I'm given f of x. So if I substitute the values 1 into the function, we know that 1 plus 1 is 2. So we get 1, 2 as one of the points. And then if I substitute 3 into the function, we would get 3 squared, which is 9, plus 3, 12. So now I have the two ordered pairs, 1, 2, and 3, 12. So then the average rate of change is going to be the change in y. So 12 minus 2 over the change in x, 3 minus 1. So we end up with 10 over 2. Or 5. Okay, average rate of change if given f of x or the x of t position, you just subtract the y's over the change in x. Okay, now let's look at an example that you might see. So we're cruising the Glacier Bay, how fun, and Lisa is taking pictures. So we are given the time that it takes to take the pictures and then the number of pictures taken. Very important to understand what is given to you. Now from the data, you want to approximate the derivative at 1.7. Well, you notice in the table, they don't give us 1.7. So we know a value below and a value above. So we are actually approximating the slope there. Now this will not be an exact derivative, but an approximation. And to find that rate of change, we would go the change in y over the change in x, minus 2 minus 1.5. And so you can see that we end up with 15 over 0.5, which is 30. Now 30 what? That means we're taking 30 pictures per hour. Now does that number make sense? That our rate of change is 30 pictures per hour at 1.7? Well, you can see we took 75 pictures at 1.5 hours, and we took 90 pictures at 2 hours. So could we be changing 30 pictures per hour? Yeah, that makes sense because we changed 15 pictures in a half hour. Okay, that's about right. Now, B asks, what is the average speed of pictures taken in the first 2 hours? Well, the average speed, if I'm given the number of pictures, then again, I would just subtract the change in y over the change in 2. And since it's over the first 2 hours, we would go 90 minus 0 all over 2 minus 0. Well, that's kind of boring. So I end up with 45. So on average, she's taking 45 pictures per hour. Okay? Okay. Now, during which portion of the trip is she taking pictures the fastest? Well, let's see. The slope here between is 20 over 0.5, okay? And we can see that this is 25 over 0.5, and then this is 30 over 0.5, 15 over 0.5, and 10.5. So definitely the greatest rate of change is in that interval between 1 hour and 1.5. That is where the rate of change is the greatest, because at that point, we would be 60 pictures per hour. Okay, now to spend this idea. Let's say that we're given, instead of the number of pictures, Ted's also taking pictures, but for Ted, we know his rate. Okay, so we're told the same amount of hours. This is the rate at which he's taking. So then we're asked to find the derivative at 1.7. Let me pause for a second. Phew, I paused it and it came back in. Okay, so now we want to find the rate of change of T pictures per hour. So this is actually asking for something a little different. Since I'm given pictures per hour and I'm going to find the slope of pictures per hour, it's like we're actually finding the acceleration, right? Because we're taking the slope of a derivative. So when I do this, 1.7 is right here. So we're going to go 45 minus 55, and then 2 minus 1.5. So the numbers comes out to negative 20, and then it's pictures per hour squared. So what does that negative 20 mean? Well, that means his rate of picture taking. So the rate of picture taking is decreasing. Okay? It's decreasing by 20 pictures per hour. Okay? 20 pictures per hour. My writing looks sloppy with this stylus, huh? Is decreasing. Okay. Now, this was similar to what you did in your FRQ today on the practice test, because we're looking at a table of data when given the rate. Now, if you wanted to find the total number of pictures taken, we could actually use our fundamental theorem here, right? And we could take the integral of the rate of his picture taking, and then that would end up with the number of pictures taken. Interesting thought. Okay, moving on along to more applications with at a point. Now let's talk about how do you find a horizontal tangent. So we are given a function, x squared minus 3x, and we want to find out if there are any tangents that are horizontal. Well, we know a horizontal tangent has a slope of 0. So we're going to find the derivative of this function, which would be 2x minus 3, and then we will set that equal to 0 to find out when that might have a slope of 0. So we can see when x is 3/2, we will have a slope of 0. And that would be the only spot. So then actually, though, to find the points, we would have to plug 3/2 back into the original equation to find the value of y. So I'm not actually going to do that math, but you can see what we would do here then to find the y coordinate. Okay? Now, if you wanted to find the vertical tangent line, you would see if the derivative is ever equal to 0, but it wasn't. Now, local linearity. So this is also another concept that we have to be able to use our derivatives for. So we're given this function, cosine squared x plus cosine of x, and it's shown below. So the curve crosses the y-axis at point P and crosses the x-axis at point Q. Now, I'm dying to factor this function because I think it's going to help me understand a little better. Because I notice there's a cosine x in common. So cosine x plus 1. And actually, that does help me a lot. Because I know here at Q, when this value has a value of 0, cosine x, when is cosine of x equal to 0? Right? We can use our zero product property. So cosine of x will be equal to 0 when x is pi-halves or 3 pi-halves. Okay, they didn't give us, They didn't give us any labels for this. So we could say pi-halves. And when will cosine of x plus 1 equal 0? Well, that's when cosine of x is a negative 1, and that would be a negative value of x. So, well, actually, cos x is negative 1 at, un momento. 0, negative 1 at pi, There we go. Pi. Okay. So since pi-half is the first x-intercept shown, then that is what is the value for q. So q is pi-half over 0. And what is the value of p? Well, if I plug in 0, cosine of 0 is 1. So 1 plus 1 is 2 times 1. So that'll be 0, 2. Can you read my writing, or is it a mess at this point? So I'm going to erase this to give myself some more room to work. Okay. Okay, now back to work. So we want to know then, find the equation of the line to f at q. So now I have the point. Now I need the slope. Okay, so what is the derivative of this function? Okay. Cosine squared of x is going to implore, nice use of that word, huh? Chain rule. So I'm going to have 2 cosine of x, and then times the derivative of cosine of x, which is negative sine of x, plus the derivative of cosine of x is negative sine of x. And I want to find the slope at the point pi half 0. So I'm going to substitute pi half in for x. Lots of good practice here with your trig, cosine of pi half. And then I'm going to have negative sine of pi half plus negative sine of pi half. So these are all facts you need to have memorized very quickly. So cosine of pi half, we know that to be 0. And it really doesn't matter what negative sine of pi half is, but we do know pi half is 1, so it would be negative 1. And then it's going to be plus then a negative 1. So then the answer is negative 1. So the slope is negative 1 at that point, and that makes sense because that looks like a slope of negative 1. So then my equation would be y minus 0, slope is negative 1, x minus pi half. We have just written a linear equation that could be used to approximate the tangent line there. Okay. Good. Okay, so now we have another function, and we've got a looks like a cubic here. And what we want to do is at x equals 4, we want to be able to use a linear approximation for 4.2. So I'm going to find the derivative, and so then the derivative will be 3x squared minus 12x plus 7, okay? And then if I substitute the value 4 into this function, I know the math, I've done it before, I get 7. You can trust me on it. So now we know that the slope is 7. So using the point then for negative 1, we can write a tangent line. So it would be y plus 1 is equal to 7 times x minus 4. So this is a tangent line where we can use that to approximate when x is 4.1 what the value will be. So 7 times 4.2, minus 4. So we get the answer is approximately 0.4. Okay, so there we go. Now, do you think this is an over approximation or under approximation? So I have this cubic function. I've drawn a tangent line to it. Is my tangent line above or below? Well, we can tell that by the concavity of the graph. So concavity of the graph. So for concavity, we need the second derivative, which would be 6x minus 12. Okay, so at 6x minus 12, when I'm looking at the point 4, is that going to be positive or negative? Well, 24 minus 12 is positive. So that means my graph is concave up at 4. So that when I draw a tangent line, whoa, that's rough, I get an under approximation. Okay? Now, what is the error in the approximation? Jeez, they want a lot of work for this. Well, if I were to actually go back to the original function and substitute 4.2 into the original function, using my calculator, I would get 0.648. Now notice, don't be distracted and circle 0.648. They wanted the error. So then the error is the difference between the actual solution and my estimate. So we can see that the error would be 0.248. Moving right along. Actually, I'm going to stop a minute to help Nina. Don't you wish you were here? Okay, on this slide, actually, what we have is the steps for if you need to write a linear equation to estimate a value. So always, first of all, you want to find the slope. Whoops, sorry about that. I wasn't in pen mode. So you're going to find the slope, and then from that slope, you'll write an equation. And with that equation, you'll approximate a value by substituting the number in. And then looking at concavity, you'll determine whether you're an over approximation or under approximation. Now the last topic that we'll be looking at is how do we find the derivative of an inverse function? Well, derivative of an inverse compared to the derivative of the original function. So let's say f of x equals a over b. So the derivative of an inverse function would just be the reciprocal of that, b over a. Okay, so if I can find the derivative of the original function, I'll just take the reciprocal. Now, on this example here, we have f and f inverse, and we're given a couple facts. We're given the point 0.35, and then we're given the derivative at 3. So f of x, then we know if we were to write an xy table, we have the input of 3 and an output of 5, and the derivative at 3 is 7. Okay, so then the inverse function would be, then we have an xy value. Remember with inverse, the x and the y values switch. So the input is 5 and the output is 3. Okay, and then at that point, we know that the derivative of this inverse function would be 1/7. So now using that point and that slope, find the correct equation. So automatically I can eliminate C and A because they have the incorrect slope. And then it's going to be 5/3. Well, E is the only correct answer. Okay, great. One more example. So here we're given f of x is e to the 3x. Now you have to find the derivative of the inverse. Well, first we have to find the derivative, and then we'll just take the reciprocal of that. So the derivative of this, e to the 3x is just itself. And then chain rule, you have to find the derivative of the exponent, which would just be 3. So the derivative is 3 times e to the 3x. Well, we know that the derivative of an inverse function is its reciprocal. Whoops, derivative, sorry guys. So it's 1/3e to the 3x. Dun, da, 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 C. And I believe that's it for today. So make sure you do your practice, and we'll be seeing you tomorrow.